Now, in our previous videos, we have seen how to use the method of corners to solve these linear programming problems. The method of corner works great as long as you're in two dimensions, as long as you only have two variables. But if you have more variables, if you have three or more, then this becomes very tedious and geometrically impossible to use the method of corners. So as an alternate method, we can look at the simplex method. This overcomes the problem of the dimensionality that the method of corners has. The simplex method is based on the Gauss-Jordan elimination method. It does not require to find all the corner points of the feasibility region that we had to do with a method of corners. So what this does is it begins with an initial corner point, and we will systematically move to another corner point until the optimal solution is found. And we will know when an optimal solution is found without having to find all of the corner points. Okay, so we're going to look at a standard maximization problem to introduce the simplex method. So a standard maximization problem is when we are maximizing this the objective function. All the variables are non-negative, and all other linear constraints are written so that the expression involving the variables is less than or equal to a non-negative constant. So we've got this less than or equal to sign in all of the linear inequalities. All right, so for example, we have this maximize the profit 3x plus 2, subject to the constraints 2x plus 3y less than or equal to 12, 2x plus y less than or equal to 8, and of course we have our standard restriction that x and y must be greater than or equal to 0. That keeps us in that first quadrant geometrically. Okay, so we're going to look at the steps here. Step one is we want to replace the system of inequality constraints with a system of equality restraints, right? So we want to convert these inequalities to a linear equation. Okay, now right now the left-hand side of these inequalities is less than the right-hand side, so we need to add something to the left-hand side to make it equal the right-hand side. Now we don't know what that is yet because that left-hand side is just variables, but we know we can add something to it to force equality. All right, so we're going to refer to these somethings as a slack variable, right? We're using these non-negative slack variables. We're going to call these u and v. All right, so if I add u, which is some unknown number, but it's the right number that forces equality, now 2x plus 3y plus u is equal to 12. And for the second one, I can add v, or some unknown slack variable. 2x plus y plus v is equal to 8. Now u and v are not known, right? And we consider them to be variables, but they are forcing equalities. It's forcing the left-hand side equal to the right-hand side, okay? All right, so that's step one, adding your slack variables. Okay, step two is taking your objective function and setting it equal to 0. Okay, so I'm taking this p equal 3x plus 2y and subtracting 3x and subtracting 2y from both sides. That results in negative 3x minus 2y plus p equals 0. Okay, and what we're doing here, right, what we're trying to get to is we're trying to get to a system of linear equations, right? Because we said that the simplex method is using the Gauss-Jordan elimination method, right? So we're going to want to put this in the form of a matrix, right? So we need this system of linear equations. So we're going to take our constraints and now our equality constraints and our profit function, our objective function, to set that up as a system of linear equations. All right, now step three, once we've done that, we can write our objective function and constraints together as a system of equations. All right, and notice how I've written this here. right? I've got the constraints first, 2x plus 3y plus y plus u equal 12, 2x plus y plus v equal 8, negative 3x minus 2y plus p equals 0. That's my objective function. And I've got that set up to where I've separated my variables, right? You can see that you can think of this as columns, right? I've got an x column, a y column, a u, v, p column, and then the right-hand side of constants. So now write this as an augmented matrix. Right? I'm just removing the variables and just keeping the coefficients here. Okay, so this matrix, putting that vertical line there for the augmented matrix. All right, so my left-hand side are the coefficients of my equality constraints and objective functions, and the right-hand side is the right-hand constant side of my equations. Okay. All right, so I've got 7 or 8 steps here. The first few steps is just setting the problem up, and then we'll actually go through how to solve this, right? So now we've got a matrix, right? Think back to chapter 5 of how we solve a matrix. We're using this Gauss-Jordan elimination method, right? And this is where we have these pivots, right? We're trying to make the first entry in the first column to be 1, and everything else in that column to be zeros. Remember that? So we're doing that, but slightly modified, because we may not always be getting this first entry to become 1. It depends. It depends on some different factors. Let's look at those different factors that we need here. All right, so we've got this matrix at the top. All right, so step 5, we want to locate the most negative entry to the left of the vertical line in the last row. The column containing this entry is the pivot column. Okay, so looking at the last row, all right, so I'm looking at this row right here. Which one is the most negative? Well, -3 is the most negative. Okay, and think about why we're looking at the most negative. And don't just follow the steps blindly. Think about why these steps are as they are. Right, this last row is the objective function. It's the profit function. Right, and we had moved that 3x and 2y to the left-hand side, and it became a -3x minus 2y plus p equals 0. Right, so now we're looking at the most negative, because that's the largest coefficient of our variables, right? So when we're looking at the most negative entry, right, we're saying that the x variable has the most influence on the profit function, right? It has the most influence. So we're looking at the column that has the most influence on the profit function. All right, so now step 6, divide each positive entry in the pivot column into its corresponding entry in the column of the constants. All right, so here's my pivot column. All right, so I'm pivoting here. So I'm looking at all my entries in the column, and I'm going to divide by, I'm going to divide each positive entry in the pivot column into its corresponding entry in the column of constants. All right, so 12 divided by 2 is 6. 8 divided by 2 is 4. Now, it's not necessary to do the last row, right, because that's the objective function. All right, I'm only interested in the equality constraints. Okay, so we divide the constant by the number in the pivot column, and the pivot row is the row corresponding to the smallest ratio. Okay, so this is the smallest ratio between 6 and 4. 4 is the smallest. So I'm going to use this 2 as my pivot. Okay, now why am I using that, right? Why am I looking at the ratios and taking the smallest ratio? All right, well, these numbers are the x-intercepts, right? If you think about, what we had done in the method of corners, right? We graphed linear inequalities, right? And we had our region of feasibility, right? And we had to find all 4 corner points, right? So now we're saying we don't have to find all 4 corner points. We just start at the most logical place, right? That's the one that has the highest influence of the profit, right? That's the x variable. And then we are taking, right, we're using this, we're using this as a pivot column. And then we have, notice that we have 2 x-intercepts. Okay, that's what these ratios are. All right, these are the x-intercepts. All right, if you were to divide the constant by the coefficients of x, that would give you the x-intercepts. And so we're going to take the smallest one, right? Because between these 2 x-intercepts, the smaller one is going to be a corner of the feasible region. Okay. So think about it in that terms. Try to relate it back to the method of corners, just to make it make sense in your head of why you're following these steps. All right, so this 2 is going to be our pivot, right? So we're going to make this 2 become a 1, and everything else in that column become a 0, right? We're still using that Gauss-Jordan elimination method, but instead of the first entry being set to 1, we're letting the second entry being set to 1 because that's our smallest x-intercept. All right, so step 7, perform the pivot operations, convert this to 1, and everything else in that column be zeros. And then step 8, we're going to work through step 7 in the next slide. Step 8, if all entries are non-negative in the last row, then we're done. Then the optimal solution has been reached. Okay, and we'll see what that optimal solution will look like, right? But as long as we have negative numbers here, then we're not finished yet. And we would need to go back to step 5 and repeat that same process. Okay. All right, so let's take a look at this using all 8 steps together, demonstrating this in the example. Okay, so we've already determined that we're using the first column. We've already determined that we are pivoting around the second entry in the first column. All right, so we want that to go to 1. All right, how do we convert that to become a 1? We're going to divide by that entry. We're going to divide that entire row by the entry 2, which is equivalent to multiplying by 1/2. Okay, so that's a 1, 1/2, 0, 1/2, 0, and 4. And we want everything else to become 0 in that first column. Okay, we can force those to go to 0 by taking R1 minus whatever we want to make 0, right? That's entries of 2. So minus 2 times row 2. And row 3, we need that negative 3 to become a 0. So we're going to have plus 3 R2. Okay. If you need to work over in the margin, let's come over here and have 2, 3, 1, 0, 0, 12. This is the R1 minus 2 R3. So we have negative 2, negative 1, 0, negative 1, 0, and negative 8. So that's 0, 2, 1, negative 1, 0, and 4. for row 1. Row 2 stays the same. And then our 3 plus 3R2. So we're multiplying row 2 by 3. So that's 3, 3 halves, 0, 3 halves, 0, and 12. 0. Negative 2 plus 3 halves is negative 1 half. 0, 3 halves, 1, and 12. All right, so now we're at that step 8 to where we said if we have all, if the entries in the last row are all non-negative, then we're finished. Okay, but if we have any negative numbers, we need to go back to step 5 and repeat. Okay, and so we see here that we have a negative entry in that last row, the second column. Okay, so that's going to be our pivot column now, because that's the only non-negative that we have. Okay, then we take our ratios. We take 4 divided by 2, and 4 divided by 1/2, which is 8. Okay, and remember, these are the y-intercepts, right? And we're going to take the smaller one because we know that's going to be the corner in our feasibility region. Okay, so this entry will be our pivot. Right? So we want that 2 to become a 1. So we will multiply row 1 by 1/2, or divide row 1 by 2. That's 0, 1, 1/2, negative 1/2, 0, and 2. Everything else stays the same. Okay, and now at this point, we want everything else in the second column to be 0. So we want this 1/2 to be 0. We want this negative 1/2 to be 0. And we can do that by taking our 2 minus 1/2 of our 1, and our 3, and then we're going to add 1/2 times row 1, right, since we got this negative 1/2. All right, so row 1 stays the same. I'm going to go ahead and write that out. Okay, let's come over here in the margin. We got 1, 1/2, 0, 1/2, 0, and 4 for R2. And then negative 1/2 R1. So that's 0, negative 1/2, negative 1/4, 1/4, 0, and negative 1. So we get 1, 0, negative 1/4, 1/2 plus 1/4 is 3/4, 0, and 3. And then our 3 plus 1/2 R1. Let's see, R3 is 0, negative 1/2, 0, 3 halves, 1, and 12. And then 1/2 times R1 is 0, positive 1/2, 1/4, negative 1/4, 0, and 1. So we get 0, 0, 1/4, 3/2 minus 1/4, that is 5/4, 1 and 13. All right, so now we've reached step 8 again. Okay, are there any non-negative entries in the last row? Now they're all positive or 0. Okay, so that's what we want. We want non-negative numbers in that last row. That's when we know we're done. Okay, now what is our solution? Okay, our solution now, okay, now remember that these were the slack variables. Okay, we really don't care anything about the slack variables. They were used just to force equality. Okay, so you can really ignore the slack variables. Now these columns do provide information, but that's beyond the scope of what we're looking at in this section for this class. So we really just want to look at the x column, y column, the p column, and then our constant, right? So we're saying that 0x plus 1y plus 0p is equal to 2, right? So y is equal to 2, and in the second row, x is equal to 3, and in that last row, p is equal to 13. All right, so 2 comma 3 gives us a max profit of 13. Now, working this using the method of corners, we would arrive at the same answer. Now, which method is easier in this case? Probably the method of corners, quite honestly, would be easier because we only have 2 variables. Okay, but we'll look at examples to where we have 3 variables, to where the method of corners would be much more difficult. You're thinking 3 dimensions, and you'd have this 3-dimensional feasibility region.